Hello, my name is Douglas Wiemer, and I'm the Chief Technology Officer for Cybersecurity for the RIA Group. And it's my great pleasure to be with you today and to make a presentation on my thoughts and considerations in regards to cybersecurity trends and emerging technologies here at the CIS 2022 Virtual Cybersecurity and Identity Summit. It should be no surprise to any of us that cybersecurity is a critical supporting aspect of all of our critical infrastructures, and how critical infrastructures themselves support the needs of our society. Of course, all of the critical infrastructures themselves provide a variety of societal benefits, ensure a sustainable economy, and deliver on cyber sovereignty and security for our nations. And cybersecurity provides an essential aspect of the underpinning of all of these different aspects that society depends on. So what I'd like to do is to provide some insights, some thoughts on cybersecurity trends and emerging technologies as it relates to how critical infrastructures come and support our society, as indicated in the last slide. One of the biggest areas of trends and direction that the industry is taking is this convergence between the cyber and physical, or the convergence indeed between information technology platforms and operations technology platforms. Critical infrastructure systems operate at this interface between cyber domain and physical domains, between information technology systems and operations technology systems. And so our operations technology processes are running on IT platforms. They're remotely managed by desktop systems. And through COVID, there's an increasing trend even to manage some of these things remotely from home environments. This creates a dependency on technology platforms that are inherently difficult to secure. Connectivity paths are complex to isolate and protect. And as a result, critical infrastructure systems become an attractive and primary target for cyber criminals. Let's keep in mind the physical infrastructure, or the physical side of this, doesn't just include perhaps the utilities, energy, water, and so forth, but it also includes, for example, operations and manufacturing control systems, food security, for example, in the domain of manufacturing, as well as other manufacturing for our core resources and the dependencies that we have on processing of our core resources. Physical security systems as well, access control and surveillance systems, are highly dependent on information technology systems. And so the physical side of this also includes the physical security. And we also have to keep in mind that more and more we use wireless systems to remotely connect to controlled devices, particularly in the domain that we operate at RIA, which is largely in the space infrastructure support. Satellites themselves have telemetry and telecommand signals that can be affected by radio frequency interference. And so wireless systems subject to jamming and spoofing become an important physical domain topic for us to look at in this convergence of cyber and physical. The other aspect to consider is the fact that these two worlds, the cyber world and the physical world, or the information technologies and the operations technologies, the governance of those domains has often been quite separate and independent, and the views of what's critical are not always aligned. And so as these two worlds come together, the convergence also leads to some interaction and conflict sometimes in the organizational governance side of things. And so from a security perspective, we need to be sensitive to these aspects and understand how we can overcome some of the barriers that may exist in the organizational and governance side of things, in addition to the system design. This all leads to an escalating need for secure systems and secure network development. Operations technologies applications really need to have a secure systems engineering and system security testing planned from the start. Our networks need to, in the operations domain, need to be supported and secured by monitoring and incident response in as much as we are already within the enterprise networks. We need to consider the role of a cyber range in the design and test of critical systems. Cyber range have, in recent years, been leveraged a lot for cybersecurity training, but more and more and more, the virtualization that is possible and the simulation and the emulation that is possible within a cyber range should be used as well for research and development to build more secure systems, as well as a pre-production environment for our critical infrastructures in order to test systems upgrades and system progress. Another area of trends and emerging technologies is the area of quantum computing. Quantum computing has the overall potential to render our foundational cryptographic processes as obsolete. Space and terrestrial network domains are responding with significant investments in quantum key distribution and quantum communications infrastructures. And that quantum key distribution really will provide a foundation for secure key distribution, but we can't forget also the issue of quantum safe, quantum resistant, or often called post-quantum cryptography. It's one thing to have a secure generation of keys, but we also need to make sure that the cryptographic algorithms that are going to use those keys are also secure. And so, of course, there's projects underway, for example, through NIST around post-quantum cryptography and the need for the post-quantum cryptography and new algorithms to be identified. Let's also not forget that there are interfaces and there are implementation issues that are going to arise, even if the quantum key distribution technologies, or let's say the algorithms and the processes, the theory behind it all should provide an increased level of security. The implementations need to be secure themselves, and so the implementations of systems, we know that complex systems lead to potential vulnerabilities within the systems themselves. So does the implementation actually match the theory? And likewise, where we have those interfaces, the diagram here tends to show, or is intended to show, where there may be interfaces, for example, between terrestrial systems and satellite systems, interfaces within the terrestrial systems. At all of these interface points, the secure distribution of keys is very important. Another trend has to do with 5G and 6G technologies. The 5G security controls are intended to address the threats and the weaknesses inherent in some of the 4G, 3G, and 2G networks. But the adoption of these new technologies always presents an opportunity for new threats. Current deployments often parallel existing infrastructures. And so you have some of the inherent weaknesses in some of the existing technologies running still in parallel with the new technologies, and that also creates the potential for weaknesses in interface points and the inherent weaknesses in some of the legacy systems. Implementations of new technologies are always new and complex, and so similar to what I was saying about the quantum technologies, anything that's new, those implementations lead to the potential possibility for vulnerabilities in design and implementation. So again, we need to look at the escalating need for secure application and systems development, and how do we apply secure systems engineering, system security testing, network security engineering, security monitoring, and incident response across all of these systems. Again, let's look at the role of a cyber range in the design and test of 5G and 6G infrastructure systems, and how can the research and development that needs to be done in these areas be further accelerated or further enhanced by the emulation and the simulation capabilities that we have in a cyber range. We also like to look at aspects of artificial intelligence-based decision support. Security monitoring and incident response technologies are growing in dependency on artificial intelligence and machine learning technologies. Inherently, there's a huge amount of data in our systems today. There's a huge amount of data that needs to be analyzed, a huge amount of data that needs to be understood, and we need to be able to identify within these vast amount of data, where are the trends that indicate anomalies, that indicate security compromise, that indicate misbehavior within our networks and systems. And it becomes beyond the capabilities of our operators today to be able to really manage all of this data and be able to filter through all of this data. And so artificial intelligence and machine learning technologies really provide an essential support to analyze and understand that data. One of the things we need to look at, though, is to what degree and at what point AI systems should be granted even autonomy to take decisions in response to perceived security incidents, or where do they need to remain subordinate to human scrutiny and supervision to guard against the potential for operational error. I think back 20 years ago in our IT systems, and the first antivirus systems, for example, were being deployed. And maybe it's more than 20 years ago now, but in any case, the antivirus systems, the early antivirus systems, you would have this screen pop up that says, this virus has been identified. Do you want to clean? Do you want to quarantine? What do you want to do? And there was constantly an interaction with the operator. Now our antivirus systems operate largely autonomously in the background. Even today, our endpoint detection response, network detection response, and our XDR systems are able to provide levels of automated containment for many, many issues. And so they have a certain level of automated response. Our SIEM and our SOAR technologies have the potential to automate incident handling playbooks. The question still becomes, at what level, right? And so where do we decide? And I'm not here to give a specific answer, but just to highlight that these are things that we need to consider as cybersecurity practitioners, as we look at how artificial intelligence is being used more and more as a support in our decision, right? As a decision support system, as we look at larger and larger amounts of data, which is only going to increase. Our dependency on these kinds of tools is only going to grow. We need to think critically about these questions. Another topic has to do with supply chain security, security in manufacturing, and Industry 4.0. Modern society is highly dependent on complex supply chain of component parts from one level to another. I think, for example, of the automotive industry. The automotive industry has a huge multi-layer supply chain of component parts that come together to deliver a vehicle, a car, a truck, something. And this is only one example, but this happens in multiple different industries. Pretty much everything that we use today, every appliance that we have, all of these things go through some kind of a multi-chain assembly line, which is no longer just an assembly line. It's an assembly line of parts that come from different areas. And very often these parts require very precision manufacturing. And so that process of making sure that the original part supplier has the design for what that component needs to look like, depends on a secure exchange of information between and to and from component suppliers. And so there's a huge potential there for intellectual property theft, which itself has its own implications. But then there's also the potential for subversive modification in that design and manufacturing information, which could ultimately affect overall the delivery of systems and solutions. Then we have to consider as well Industry 4.0. Industry 4.0 has a huge potential to improve the precision and reliability of the manufacturing process. Secure exchange of manufacturing data, though, is necessary, right? There's design data, there's build data, there's manufacturing process data, there's performance data, there's reliability data, and so forth. All of this is now creates an interconnection between the manufacturing floor and the original equipment manufacturer that produces the tools that are used to provide the assembly and the manufacturing. And so this increases the attack surface of the manufacturing process. And there's a trend in increase in attacks in these manufacturing capabilities. One of the areas that I'm really intrigued by is this whole area of non-fungible tokens. Non-fungible tokens are a byproduct of the blockchain and the cryptocurrency technology domain. It's currently dominating in many ways the cryptocurrency as a means of securing digital information. And that in and of itself triggers some ideas around how can that then have potential benefits for the digital data that is inherently needed in these manufacturing processes, right? So if we think of model-based systems engineering and the exchange of digital files, can we somehow use the non-fungible token process technology as a means of securing our model-based systems engineering, our manufacturing processes, and Industry 4.0? I think these are all areas that should be investigated. So I'd like to thank you very much for this opportunity to share some thoughts and ideas. Hopefully you find it interesting. Thank you very much.